Hello everyone, this is a low-tech demo whereby I send screenshots and big JSON files through GitHub. Thanks for your patience while my laptop didn't want to work. As I have been introduced, I am Nadri. My main interaction with Rust is being a compiler contributor, but in my day job I also do Rust. And today I'll present the project we do at work. I'm building Charon, which is a tool that tries to help you get everything from a crate to analyze it. Specifically aimed for semantic kind of analysis, where you want to see what code is being run, rather than syntactic analysis where you want to do lints. We don't do that. We do semantic. And so you run. It's a binary. It's a project. You run it on a crate like cargo. It's called Charon, and it extracts everything into a big JSON file. So I will do a demo, explain some of the things we do, so you don't have to do them yourself. Some examples of what we built with it and where the project is at. And now to the extremely amazing low-tech demo. I'm literally this is in my test suite now, so hopefully you can read that. Go away here. This is an example bit of Rust code that showcases some of the things we can do with Charon. So normal Rust code, and then let's see if I can get to the output file. All right, two things that Charon does. You will run Charon in a crate. We'll give you a big JSON file. This is the big JSON. Oh, this is too formatted to be legible. We'll see if we can find something legible. Whatever. The point is, I will. Oh wait, the demo, the Charon README has examples. Am I that good? Okay, that's the idea. Yeah, that's why I wanted. So the JSON looks like this. You basically get a bunch of lists for everything that's in your crate. You've got, including dependencies, right? Like recursively, every code that you might need to execute whatever is in this crate will be included. You've got the definitions of types. You've got the traits, imps, and declarations, and the functions. And when I mean functions, I mean everything you need from a function: the function name, signature, function body. And it's all a pretty simple AST. If we had a JSON, I could show you. I guess I could show you the docs if you want to see the AST. I'm improvising here. Here's the docs. Let's see. Will it work? Oh yes. Thank you, rustc. Rustc is great. Where's translated crate? Here we go. This is the JSON that I dumped with 30, right? It has the lists we mentioned. So what's a function, for example? Here's a function. Function declaration, what does it have? Item meta is where I store things like the name of the function, whether it's public or not, some other attributes you might have on it. I've got the signature, which is literally just input, output. We've got the body. Well, it's all very simple kind of AST, and I've got a pretty printed output, so you can actually read what's in it. Let's see. Yeah. What do we got? My function, remember, that was just a simple function that took a slice of T and debugged every element in turn. Some of the things you can see is, well, this is verbose, but this is precise. This is basically the mir. Except instead of having gotos everywhere, you might notice we have loops and ifs and branches. So the control flow is structured. So if you want to, if that simplifies your analysis, that's good. It also, we're trying as best as we can to resemble the code that was written as user code. If you want to translate it to something legible, which is one of the things we do. You can see here there's a call to into iter, here there's a call to next. And like this is a very big name of the function next for this particular impl, right? And you can find it if I can scroll it. It's probably one of those, right? It's one of those. The body is not here, but I could include it with a flag. And the last thing I want you to notice is here. This is generic code. The function was generic, right? This is polymorphic code. It's polymorphic in T, and we're making all the trait clauses explicit. All the trait is made explicit. It's basically dictionary passing style, if you know what that means. So when this function is called in the main function, it will be provided the implementations. Where's the main? That's the main. The function is called here, and it is given explicitly, this is the impl we use, which is debug for I32, right? So all the traits are explicit, so you always know exactly what code you're calling. Back to the slides. That's not my slides. Where are my slides? This one. Yes, that's my slides. Right. So some of the things we do. The point of Charon is it's simple, and you never have to look at rustc internals, right? Many projects that want to analyze Rust code have to delve into compiler internals. They're not very well documented. They're full of tricky implementation details, and they're full of tricky edge cases. So what we do in Charon is trying to centralize that work. So we're contributors as well, but mostly me. I poke at the internals, I resolve the edge cases, and you never have to think about it. So some of the things we do, it's just plain a simple binary, and then the crate that reads, it's just the crate with the types I showed you. It's just a bunch of types 10 sud. There's nothing fancy in that crate to read the JSON. Simple AST. The semantics are accurate. We're taking the mir, so it's as accurate as Miri would in terms of exactly what we're executing, but we're reconstructing control flow, as I mentioned. So we get loops and ifs. That's optional, but that's a selling point. The code is polymorphic if we wanted to. So we track all the traits, which is one of the main crazy things we do. But that's needed if you actually want to know what code is being run. We have someone contributed recently in the last 3 months a path to monomorphize everything. So if that's your jam, we have that. Constants. This is almost not an in-joke, but everyone who's tried to write a rustc driver will know. I hear some laughs. Constants are a pain in rustc. There's a bunch of different constants. They can be evaluated or not. Like actually extracting what the expression is supposed to be is a pain. We do that. OCaml bindings for it turns out that about all of our users use it through OCaml, because the sort of the community that does analysis and verification of code is quite keen, especially in France, where I'm from. It's quite keen on OCaml. So we have OCaml bindings. So you can use that, and that's it. That's some of the. We've got more selling points. The point is mainly just centralize the work. So if there's some cool thing that you want Charon to do, you can contribute it, and then we only have to do it once. Some of the things we've built with it. The first is a tool called Eneas. That was the origin story of Charon. It was developed at the same time. It's a tool that translates Rust code into purely functional code, specifically for proof assistance, if you know about these. And with the aim of proving code, like safe Rust code only, safe Rust code with the aim of proving, doing like interactive proofs on your code. That works decently well. We've got Eurydice, which translates Rust code to legible C. The constraint being that outputted C needed to be actually committed and looked at least legible enough that someone can see that looks like the thing we wanted. And it's for big companies. I don't know if I can say which companies, but companies that wanted some good Rust code to be compiled on some targets included in some built system that didn't yet support Rust. We've got Rodra, which is Rodra was a project to analyze to detect unsafe to detect bugs, unsafe bugs in a bunch of crates. That was rather successful in finding bugs, and we re-implemented it in top of Charon because why not, to just see if it worked, and it worked it was very simple. Charon on Charon is I actually used Charon on itself to list all the Rust types, so then I can translate them into OCaml for the OCaml bindings. That works super well. Charon is a decent tool for reflection. Once it fits stabilized enough, I think it might replace rust.json on some things. I hope it doesn't, but I know people will use it. And the final is a collaboration with Imperial College team to do some symbolic execution of code to detect some UB in a clever manner. And they're pretty happy with it, as far as I've heard. So very quickly, the status is that it works pretty damn well, and it's still a moving target because we're adding more things. Like right now, I was working on adding resolving drops, so we know exactly what code is being run on drop. This is not trivial, especially in polymorphic code. But if I've finished that, then Charon will know. And I don't think any other analysis tool of Rust today handles drops correctly. Tell me if I'm wrong. It's evolving, but people are building on it, and that is good enough for that at the moment. Contributions welcome. Come chat, and come chat to me afterwards if you wish. I've got 5 more seconds, so here's the summary. I poked at rustc internals, so you don't have to. Let's centralize the effort if we can. This is all obviously open source and funded by public money from France. We love it. Thank you.